を刺激する生足魅惑の雨よ出すとこ出してたわわになったら本物の恋はやれそうかごまかしきから次の曲さは確信反応しなやかなさい愛水性の気持ちに切り替わる瞬間の眩しさはいかがなもの心まで脱がされる熱い風の誘惑に負けちゃって構わないから真夏は不祥事も次第で妖精たちが夏を刺激する生足魅惑の雨よ出すとこ出してたわわになったら本物の恋ができそうか妖精たちの夏をしたくなる脱力は終わっちゃうねよ出すもの出して素直になりたい君と僕となら It's alright刺激する七足へそ出しま雨よ恋にかけてお留守になるのも大好き的にも All OK 女性夏を誰としたくなる一人目の夜に行かせる僕のこの場で乾くまないほど本物の恋をしませんか本物の恋をしませんか
Okay, so welcome back. Let's see here. As I was saying in chat, your exam this Friday will go up through chapter 6. So we'll finish chapter 6 today, hopefully. If not, then it'll take like maybe 10 minutes on Friday to finish it. But it'll go up through chapter 6. No chapter 7 stuff until the final exam. So anyway, so that's the deal. Like I said, I'll post your exam to, I don't know, some like after the afternoon of Friday. So it won't be too bad. It'll be about the same as the last exam in terms of structure and length and all of that. So anyway, we did Gram-Schmidt process last time. Maybe I should pull that. Let's see. I have my sheet here. Here we go. So just so that, if you're watching this video and you don't want to go back to the other video, you can see, here's the Gram-Schmidt process. We did one example of this, which is pretty much the only example you need to see because all of them work exactly in the same way. There's kind of not that much that can happen. So last time we found an orthogonal basis in this way. So remember, Gram-Schmidt, what is the main purpose? Well, literally the only purpose, exactly what it was designed for. We start with a basis and we get an orthogonal basis. So we start with a basis for some subspace or for the space itself, and we get an orthogonal basis. Okay. Of course, once we have an orthogonal basis, we can, on our own, get an orthonormal basis. It doesn't depend on Gram-Schmidt at all, right? So this part we can do regardless. If we have an orthogonal basis, we can always do that. We don't need to know Gram-Schmidt. It is cumulative in the sense that it doesn't really make, this is not really a topic that breaks up nicely like Calc 3, where, in Calc 3, like you're doing partial derivatives in one, and then in the next section you're doing like iterated integrals, and it's just easy to split up the exams like that. But with linear algebra, it's just permanently cumulative always, right? Because once you know what a determinant is, it's like if I ask you any question about whether or not a matrix has an inverse, well, you need the determinant, right? It's just because the determinant's in chapter 3 doesn't mean you are not going to use it later. But that is kind of the same way for absolutely everything we did. So, basically what I can say is that, exam 2 is going to focus on the stuff we've did since exam 1, but no, like all of that stuff that you needed to know for exam 1, you still need to know for exam 2. And that's going to be how this course, it's not just the course, it's just how the material is. It's just permanently cumulative. Okay, what this is going to allow us to do, the fact that we can start with basis and get orthogonal basis, it is going to allow us to Qr factorize a matrix. Okay, and so before I even talk about what that is, I'm just going to write it as the theorem because the theorem explains what it is. So Gram-Schmidt gives us Qr factorization. I still get nervous whenever I hear Qr factorization because when I took this class, I had an instructor that was not that fair. And so I might have mentioned previously that we had to do computations by hand where no effort was made to make the computations even remotely nice. So, I ended up with entries in a matrix that were like 5-digit numbers over 6-digit numbers that I had to compute by hand. But other than that, I'll never forget that we were given a problem on an exam to do a Qr factorization for a matrix that was big, like pretty big. I can't remember. I think it was like a 5 by 5. Anyway, it took me literally like 45 minutes to do it by hand, and it was a single problem. So I still remember that problem. It was terrible. So let's say A is an m by n matrix with linearly independent columns. So if A has linearly independent columns, let's say A has linearly independent columns. Then A can be factored. I'll put this in quotes, as A is Q times R. This is why it's called the Qr factorization. Okay, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A. So the columns of Q are an orthonormal basis for the column space of A. Okay. And R is a square matrix that is upper triangular. This is an upper triangular invertible matrix. Invertible, trying to fit that word in. Matrix with positive entries on the diagonal. So that's a very special matrix. It's a square upper triangular invertible matrix with positive entries on the diagonal. Of course, if you knew that it had positive entries on the diagonal, you'd know that it was invertible. Why is that? Well, I mean, there's a lot of reasons why you could say that. One of the reasons is that if it's upper triangular and it's got positive entries on diagonal, I know that those positive entries would be its eigenvalues, and I know that the determinant of, a matrix is the product of its eigenvalues, and so it has determinant non-zero. But, right, I didn't need to do that. I could have just said the determinant of the thing is product of its diagonal entries anyway, right? I didn't need to reference eigenvalues at all. So product of diagonal entries are the determinant of the matrix, which is clearly non-zero. Okay. So anyway, so you could forget this invertible word if you know that it has positive entries on its diagonal. Anyway, so this is the deal. So A can be factored as Q times R, where Q is an orthogonal matrix if it's square, of course, but it's a matrix that has orthonormal columns, and they form an orthonormal basis for the column space of A. Q, so Q is a very, very nice matrix, right? In fact, recall Q is going to satisfy all those really, really nice facts that those matrices with orthonormal columns satisfy. Okay, I was looking for the sheet over here. I don't think I have it. I think I already got rid of that one, unfortunately. Okay. And so, obviously, like, you're saying that this A can be factored as Q times R, where Q and R are both really, really nice matrices in some way. No, and R doesn't need to be fully diagonal, just upper lower triangular for the diagonal to be the eigenvalues. That's right, Gustavo. Yeah, it doesn't need to be diagonal. That's true for triangular matrices. Okay, so then this could be said as, A can be factored as two really, really nice special matrices, right? One that's always square, one that's not necessarily square if A is not. That it's the same size as A, that is made up of orthonormal columns. Okay, so you might guess that this has something to do with the Gram-Schmidt process, because if I'm finding this Q, this involves taking linearly independent columns of A, that of course are a basis for the column space of A, constructing the columns of Q from that using the Gram-Schmidt process. And then I'll talk about where R comes from. In fact, maybe I'll consider this the proof of this statement. So here's Qr factorization again. All right, so the proof of this is the process. Well, what's the process? So one, the columns of A, well, maybe I should write the process again so that it's even clear what I'm doing. So the Qr factorization of A. So the columns of A are linearly independent. That's the assumption. If they're linearly independent, the columns of A are a basis for the column space. So I know that in general, right, the column space of a matrix is just the span of all the columns of A. But if the columns of A aren't linearly independent, then some of them are redundant, right? And I would typically have to throw some out before I got a basis. But if the columns of A are linearly independent, then they are a basis, right? The columns themselves are a basis for the column space. So the columns of A are a basis for col A, since they are linearly independent. Okay. Now, they're not necessarily orthogonal, of course, but now we have a basis for col A. By Gram-Schmidt, so using Gram-Schmidt, I can construct an orthogonal basis for col A using the columns of A. Right. Then I can scale these to form an orthonormal basis for col A. Right, this I can do from any orthogonal set, but I can clearly do it here. So I scale each one of these by their length. Okay. All right. Now I have an orthonormal basis for col A. These are the columns of Q. Right. Now, what order are these columns of Q in? They're in the same order as the columns of A. Right. Okay. So they're in the same order as the columns of A. All right, so that is what's specifying your order there. Okay, so now we use the fact that that Q has orthonormal columns, i.e., what was one of the list of facts? So I didn't have a sheet having this list of facts, but this was one of them. Or here's the full list. Of course, I listed some other things too, but there we go. Is that slightly blurry? So here, I'm going to make it close. So one fact was an m by n matrix U has orthonormal columns if and only if U transpose U is the identity. This is what we want to use. There is also these nice facts as well. This is all really, really, really nice stuff. But right now, this is the one we want to use. Okay, the fact that if you have a matrix, m by n has orthonormal columns, it means U transpose U is the identity. Okay. All right. i.e., Q transpose Q is equal to the identity. How does that help? Well, that helps in a very specific way. In that if I'm looking for A, which is supposedly QR, right? So if A is QR, then what is Q transpose A? Well, it's equal to Q transpose Q times R. Okay, but Q transpose Q is the identity. So this is the identity times R, which of course is just R. Thus, the R that we seek, that is, if you check the dimensions here, has to be, so this is Q transpose times A is M by N, Q transpose is N by M, so the resulting product is N by N. So R, which is guaranteed to be an N by N matrix, is Q transpose. So you found Q by step 3. You start with A. When you do this multiplication, you are guaranteed to get an upper triangular matrix with positive entries on the diagonal. So this gives you R. Okay? So that does it. All right. Okay. So let's see an example of this using the same numbers from the last video. Okay, so if you want to see that example over again, you can watch the previous video, lecture 29, where we come up with some of these numbers. And so my single example finding a Qr factorization is the following. So find a Qr factorization. The matrix A, which is the 4 by 3 matrix 1, 1, 1, 1, 0, 1, 1, 1, and 0, 0, 1, 1. Well, note that the columns of A are the three vectors x1, x2, and x3 from last lecture, right? So from last lecture. Okay, and so this was the example of Gram-Schmidt that we did last lecture. So by Gram-Schmidt, we previously found that applying Gram-Schmidt to the vectors x1, x2, and x3, which are a basis for the column space of A. This led us to vectors we called v1, v2, and v3. Of course, in our example, we used a scaled v2 we called v2 prime, So we had V1, V2, and V3, where V1 was found to be 1, 1, 1, 1, right? That's Gram-Schmidt first step, right? So V1 was the same as X1. V2 prime was minus 3, 1, 1, 1. Right, we'd scale that by 4, I believe. And V sub 3 is 0, minus 2/3, 1/3, 1/3. Now, in the first, in our last example of Gram-Schmidt, we stopped there because that was the last step, was to find this last vector in our orthogonal basis. But since we're going to do more with this, now we want to scale this as well, right? We automatically, as I said, right, you can scale these vectors in an orthogonal set, doesn't upset the orthogonality. And so these form an orthogonal set, right? And you can just check that they're orthogonal. So they're an orthogonal basis for the column space. So I can scale V3 for convenience. And so I can replace it by what I'll call V3 prime, which is 3 times V3, right? Which is just 0, minus 2, 1, 1. All right, these are little tricks, of course, that are not as important when you're doing things online with access to all kinds of things, but when you're actually doing this by hand or you're doing it as a part of a quick example, this is a nice trick to have. Okay, so now what do we do? This is an orthogonal set, but it's clearly not orthonormal. For instance, the length of this vector is the square root of 4, right? So it's 2. So the length of this vector is 2. That's no good. That's not a unit vector. And so I need to make this an orthonormal basis and put that as the columns of Q, right? So I then scale each vector by its length and form Q, right? And so to do that, I would scale V1 by its length. I already said the length of V1 is square root of 1 squared plus 1 squared plus 1 squared plus 1 squared, so it's square root of 4. So 2. So this is 1/2, 1/2, 1/2, 1/2. The second column is V2 prime scaled by its length. So what is the length? This is square root of minus 3 squared plus 1 squared plus 1 squared plus 1 squared, so 9 plus 3, so square root of 12. So this is minus 3 over root 12, 1 over root 12, 1 over root 12, 1 over root 12. Okay. And then lastly, I don't want to deal with, this is exactly why I scaled this, I don't want to deal with how nasty that would be. So here, what is the length of this? This is square root of 0 squared plus minus 2 squared plus 1 squared plus 1 squared. So this is square root of 6. And so this is 0 minus 2 over root 6, 1 over root 6, 1 over root 6. And so there's my Q. All right. Okay. And so now I need to find R. But to find R, I recall that I find R by multiplying Q transpose in A. Right? So that's all I have to do. Now I'm not going to go through that whole process. I'll write this out though. So R is Q transpose A, which if you actually write that out, what you get is the matrix reading row-wise 2, 3/2, 1, 0, 3 over root 12, 2 over root 12, 0, 0, 2 over root 6. Note it is, it's upper triangular, has positive entries on the diagonal. And you can check, if you really wanted to, you can check that A is equal to Q times R. Okay. All right, and so we factored A like this. Now, you might say, okay, what is the purpose of QR factorization other than just saying, all right, I can write A as a product of two really nice matrices? It turns out that if you have a QR factorization of A handy, it allows you to more or less immediately solve several numerical things that you might want to do, or several application problems that you might want to consider for A. So having the QR factorization is really nice. Okay, yeah, QR factorizing is a very, very nice thing. And so we'll have one application of it in the very next thing that we talk about, which shows how nice it is. Anyway, okay, so that's that. That's QR factorization. So there's one more topic that I want to discuss in Chapter 6, and then we will be done. And that is what are called least squares problems. Okay, we'll see why it's called least squares. It's because we're minimizing a distance, and we know that minimizing a distance means if you're talking about distance or length, right, then computing a length is square root of some sum of squares, right? And so minimizing this quantity means minimizing this sum of squares, and hence least squares. Okay, now what is the idea here? So the idea is, suppose I want to solve ax plus b, or sorry, ax is equal to b. Right? I joked at the very beginning of the semester that the entire course was that single equation, and that's still basically the case, right? Because it's now, we don't have much time left in the semester, and we're still talking about the equation ax equals b. So suppose that I want to solve ax equals b. Well, you know that there's several options here, right? This bifurcates, right? And this bifurcates into, well, I shouldn't say bifurcate, it trifurcates, right? Because there's three cases here. There's the case where we have a unique solution. There's the case where we have infinitely many solutions, and there's the case where we have no solutions, right? Now, if I want to solve this, I'm perfectly happy with either of the cases where I have a solution, i.e. I'm happy if it's consistent. But I know that it's possible this is inconsistent, right? So suppose I want to solve ax equals b, but it has no solution, right? It is inconsistent, right? It has no solution. Okay, but for whatever I really need to do, I still really want to solve it. It has no solution. That's terrible luck for me. But nevertheless, I want to solve it because the solution to it would be nice for me. Now, it doesn't have one, okay? So I can't find a solution to it. But maybe I'm happy with something that is close to being a solution, right? But then also suppose that I'd be happy finding a solution, or finding a vector x, we'll say x hat, I'll call it, that is almost a solution to ax equals b. Now, what do I mean by almost a solution? Well, we'll talk about that here in a second. There's no standard here for being almost a solution. We're going to have a very specific, precise language that says exactly what we mean here. And the idea is that if this thing is a solution, right? If x is a solution to ax equals b, then ax minus b is equal to the 0 vector. All right? Oh, maybe I'll give myself more room. So note, if ax is equal to b, right? That is, if ax is equal to b for some x, that is, we have a solution, then ax minus b is the 0 vector. Then the length of ax minus b is 0, right? In fact, this is the only vector for which I have length 0, right? The only vector that has length 0 is the 0 vector. Okay. All right. So if x is not a solution to ax equals b, then the length of ax minus b is positive. Right? Length can only be either 0 or positive. It's only 0 when you're dealing with the 0 vector. So if ax minus b is not the 0 vector, its length has to be positive. Right? And so what is the idea of a least squares problem? And the idea behind least squares I want to make the length of ax minus b as small as possible. Yes, so it's minimizing that length. Gustavo said it in the chat. So minimizing that length is what I want to do. So I know that it's not going to be 0 in my case. I can actually include the case when it is 0 in all this, and in that case, my least squares solution we're going to talk about is just the actual solution. But typically, the entire point of talking about a least squares problem or a least squares solution is that you begin with an equation that is inconsistent. Okay. So, sorry, my cat was freaking out. It had an itchy chin, and I had to go over and scratch it so that it would stop meowing. Okay, so anyway, the idea here then is that the least squares solution allows for you to talk about being as close to a solution as you possibly can be, okay, without actually being one. And this is nice if you're talking about, if your solution to an ax equals b thing has some application, right? And you're not satisfied with just saying, "Oh, I have no solution, so I'm just giving up and I'm not inputting anything," right? That's the idea here. Okay. The idea, show the cat if possible. I think I already showed this cat maybe earlier in the semester. So here she is. She's really fat. Okay. She's unhappy. But there she is. Okay. All right. So, anyway, this is like, think of an example like this. This is not necessarily something you would do with least squares, but here's an example, right? It's, say that you have a problem of path finding around like a tree, right? If you wanted to set up some kind of automation of computing a path that's like broken lines around a tree, if you had 2 points in the trees exactly, right, lies smack dab in the, along a line determined by those 2 points, then you can't pass through the tree. So you have to go around it. And so there's no solution that minimizes that distance, right? There's no solution that actually gives you the line segment between those points. So you've got to go around it in some way. So you have to, you still got to, just because you have this obstruction in your path doesn't mean you can't go from A to B, you just do it in a suboptimal way, right? That's one example of where you're not happy just saying, oh, there's no solution, so that's it. Okay. All right. And so, yeah, let's, I was trying to gauge whether or not I have enough room. I think I have enough room for the definition here at least. So, definition. So this is a definition of a least squares solution. So this is a least squares solution. So if A is an M by N matrix and B is in Rm, a least squares solution of Ax equals B is an X hat that is in Rn such that the length of the textbook writes it in the opposite direction. It doesn't matter. It's you have the length symbols around it. It doesn't matter what order this is. So the length of B minus Ax hat is less than or equal to the length of B minus Ax for all x in Rn. Okay. And so what this says intuitively, of course, is X hat minimizes the length of, say, B minus Ax among all x in Rn. And that's a short and sweet way of saying the same definition. Right. So the thing here, right, is particularly nice because it allows us to talk about a quantity that in some sense is like as close to a solution as we get. Okay, and this notion of being as close to a solution as we get is something that it turns out we can always talk about. And so a problem, even if it's inconsistent and has no solution, it's going to have a least squares solution. Okay, and what is required to get you there is almost no assumptions. Okay, and so to see this, what is the idea? There is an entire. I think I probably have exactly enough time to do this. So I can actually go through the reasoning behind this. I don't have to just slap the formulas up or the process. So how do I solve a least squares problem? That is, how do I actually find this least squares solution? Okay. Well, remember that we're thinking about this as an approximation, right? So this is an approximate solution. Why am I focusing on the word approximate here? Well, there was something that we did fairly recently, i.e. maybe just like one lecture ago, that had the word approximate in it. At least it was a root word of something in it. Right, what was that? So note we are approximating a solution to Ax equals B. So wouldn't it be smart to use the one theorem that we have in this class that has the word approximate in it, which is the best approximation theorem? All other approximation theorems are inferior to the best approximation theorem. So this is the best one you get, right? It says it right in the title. So let W be a subspace of Rn, let Y be a vector in Rn, let Y hat be the orthogonal projection of Y onto W. Then Y hat is the closest point in W to Y in the sense that the length from Y to Y hat is less than the length of Y to any other vector in the subspace. Okay, you might have immediately thought about this, not from the name, but the second that I wrote out inequalities involving these length or distance quantities, you might have had this thought that you had seen this, just in the previous lecture. So here it is, okay? Here's what I want to use. It's that orthogonal projection was the thing that I did to give me the point in my subspace that is closest to this other point that's not in the subspace, right? And what this is telling you, right, is thinking of a point not in a subspace and a point, finding closest point in a subspace, we could recast that entire thing as the subspace is going to be the, say, column space of the matrix in question. Then the solution to AX equals B is associated to the subspace that is just the column space of A, right? And whether or not a vector is in the column space then becomes whether or not the vector is in the subspace. If it's not, we project onto the column space. That's the idea here. Okay, and to see how that goes here, what's the idea? So given A and B as previously stated in our definition for a least square solution, we apply the best approximation theorem to the subspace W equals the column space of A. So essentially what we're doing is we're going to project onto the column space, and it turns out that that actually has a really nice form that takes. Okay. All right. So we project onto the column space. Let, say, B hat be my projection of B onto the column space of A. Okay. All right. If you quickly lose sight of what's going on, like pictorially, or if you think about it in terms of these orthogonal projections, I'll show you a couple pictures here in a second. Okay. All right. Now, what do we know, right? Well, B. The idea here is that we kind of want to apply this in the case that this doesn't have a solution. So B may not be in the column space of A, right? That's kind of the whole thing. If B is in the column space of A, then this has a solution. But B might not be in the column space of A. But B hat is the projection of B onto the column space of A, right? Note, B hat is guaranteed to be in the column space of A, right? By definition. Because you're projecting onto the column space of A, and when you project a vector onto the subspace, you get a vector that's in the subspace, whatever that is, right? So this, even if B is not in the column space of A, it projects onto something that is, right? So B hat is guaranteed to be in the column space of A, i.e., the equation AX is equal to B hat is consistent. Always. Right? That's just another way of saying that B hat's in the column space of A. Okay. All right. Thus, there exists an X hat, right, in Rn such that AX hat is equal to B hat. Right? That is this solution, right? One of these solutions, we'll say, to AX equals B hat. Okay. Now, by the best approximation theorem, right? Now, B hat is the closest point of call A to B. Right? So B hat is the closest point in the column space of A to B. Thus, any vector x hat is a least square solution to ax equals b if and only if x hat, that is a x hat, is equal to b hat. Oh, I am off the page. There we go. All right. But how would I find this x hat? All right. Well, the idea is, suppose x hat satisfies this equation. Ax hat equals b hat. I then use the orthogonal decomposition theorem Do I have the paper for that? I do. Recall orthogonal decomposition theorem. So if W is a subspace of Rn, then each vector in Rn can be written uniquely in this form, right? That this is my generalization of the nameless theorem. That is a sum of a vector in W and a vector in W perp. And moreover, this orthogonal projection can be written exactly as this linear combination of an orthogonal basis for W, where the weights are this nice form that we get from the orthogonal representation theorem. Okay. So then I use the orthogonal decomposition theorem, right, to figure out what is true about this B hat and B, right? So then I use the orthogonal decomposition theorem to note that B hat, which is a projection, right, the orthogonal projection of B, is such that B hat minus B, this would be the Z, B minus B hat or B hat minus B, however you want to do this, is perp. It's orthogonal to the column space of A. What does this mean? Well, thus, here comes the important fact that's going to get us to the home stretch. So thus, B minus AX hat, B minus AX hat is orthogonal to each column of A. Okay. Thus, so first of all, where does this fact come from? Maybe I'll go back here. Previous page. This difference in vectors, this is my Z from the orthogonal decomposition theorem. This is perp to the column space of A. And so this means that this B minus AX hat is orthogonal to each of the columns of A. So thus, if say AJ is a column of A, then what does it mean to be orthogonal? It means their dot product is 0. Right? So then AJ dotted with B minus AX hat is equal to 0. But another way of writing this, right, rather than writing it as a dot product, remember that for a dot product you could actually write, right, instead of writing two vectors dotted with each other like this, you could write this as VI transpose times VJ and use matrix or matrix multiplication, right? Here, treating those as transpose matrices. Okay, and so what does this mean? So if AJ is a column of A, then AJ dotted with B minus AX hat is 0, i.e. AJ transpose times B minus AX hat is equal to the 0 vector. Or sorry, is equal to 0. Still not the 0 vector. This is a dot product. Okay. But AJ transpose is a row, right? So it's a row of A transpose, right? So AJ transpose is a row in A transpose. Thus, this statement says what? This statement says that A transpose times B minus AX hat is equal to the 0 vector. All right, so now I've moved from dotting individual columns like this, rewriting it as my columns transpose, which are rows in the transpose matrix, and then I've moved from that, dotting the individual columns, all those are 0, so then we get the matrix equation A transpose B minus AX hat is equal to 0 vector. Now we're cooking. This is exactly what we've been looking for. So now this is A transpose B minus A transpose A. X hat is equal to the 0 vector. And this gives us the following. This is exactly what we've been after. A transpose A X hat is equal to A transpose B. Any least square solution would have to satisfy this. In fact, we can also go backwards. These are called the normal equations. And so this actually solves our problem entirely. So our big theorem that tells us exactly what to do with least squares problems is that the set of least square solutions to AX equals B are coincide. This coincides with the non-empty set of solutions to the normal equation A transpose A X hat equals A transpose B. And what's amazing is that the normal equations always have a solution. They're always consistent. All right, you can think about why that is, but that's the case. And so, what's the process for finding the least square solution? The process for finding the least square solution is solve the normal equations. That does it. Okay, and we're happy with any solution that we get from the normal equations. Under certain situations, the solution will be unique. Okay, so I have 2 more facts to say. It'll take me about 10 minutes on Friday, and then we'll be done with Chapter 6, and that will be it for the material on your exam. For the rest of the time on Friday, what I'll do is I'll start on Chapter 7, and I might take, like a good 5-10 minutes, and if you have any lingering questions about the material since the last exam, you can ask me in chat, and I'll go over those. But other than that, we'll start on Chapter 7, and then I'll post your exam in the afternoon, and it'll be due the week after. So anyway, that's the plan. So I will see you all Friday.